And I will have to reshare my screen because it timed out. Okay, so now that we concluded PD controller, now let's take a look at as our case 3. Again, let's visit the integral controller. Okay, integral or I controller. It's not very often used by itself. Often it's combined with other modes, but still we can see that it's still by itself may generate kind of an acceptable behavior. Okay, so by itself it looks like this. So our GC of S in this case is Kc over tau I times 1 over S. Okay, so this factor, a combination of the actually this Kc, it doesn't mean anything by itself in this case because we don't have a proportional mode, but let's consider that Ki, the integral gain, is a combination of Kc and tau I again. It will become more meaningful when we combine it obviously with the proportional gain in a minute. Okay, so what we have here is Kc of S, Gc of S, G of S becomes simply Ki over S times S plus 1, S plus 2. Okay, so the most obvious effect of this is that now we have a type 1 system. Okay, so for a unit step input, ESS equals 0 for unit step reference. Okay, so by adding an integral controller, let me open my video as well. By adding an integral controller, the most obvious impact on the system, or let's say most obvious desirable impact on the system, is that it makes straight away, it makes the steady state error for a unit step reference equals 0. But still, you know, this is a desirable effect, but we need to be aware of other effects. Okay, but we need to be aware of other effects on system behavior. And for that, we will again look at as we play with Ki. Okay, so what's happening with Ki? Let's again take a look at let's consider the root locus again as we change this parameter Ki. Okay, so what we have is that what is the number of asymptotes? Now we have no zeros but 3 poles. Okay, so this is n minus m absolute value is equal to 3 asymptotes. What are the angles of the asymptotes? Well, we have basically the 360 degrees divided as such, so it's going to be plus minus 180 degrees divided by 3, which is this difference of n and m at absolute value and odd number of these angles. So what this gives us is that it is plus minus 60 degree 2L plus 1, an odd number of them. So that gives us unique angles of plus 60, minus 60, and plus minus 180 degrees. Okay, These are our three asymptotes. Well, we have the intersection of the asymptotes, which is our centroid. Remember, the centroid formula is the summation of all the poles minus the summation of all the zeros divided by the number of poles minus number of zeros. So we have the number of poles. If we add them up, one of the poles is at 0, so that doesn't contribute. So we have minus 3 minus 0, because we have no zeros, divided by 3 minus 0, because we have 3 poles and no zeros. So that gives us minus 3 over 3 is equal to minus 1. So this is the intersection of the asymptotes. So let me try to sketch the root locus in this case. This is our S-plane. We have a pole at minus 1, a pole at minus 2, a pole at 0. Okay? Intersection, the angles of the asymptotes which are intersecting at minus 1 are plus 60 degrees. So this is 60 degrees. And also minus 60 degrees. And also obviously 180 degrees. So the real axis is also an asymptote. Now I will try to sketch our root locus. This region is part of the root locus. Okay, and this region is part of the root locus. So root locus starts at the open loop poles. There will be a breakaway point here. And also this asymptote will have this branch as well. So there will be a breakaway point and we will have, okay, let me actually correctly sketch this, because the j omega crossing most likely will not be equal to where the asymptote intersects the j omega axis. Okay, so j omega axis crossing, and although I will not find it, it can be found if you remember. Okay, also there will be a breakaway point also can be found, which I will not do here. Okay, so here is what we see as what happens, right? This ki starts from 0 at these points, the open loop poles, ki equals 0. As ki goes to infinity, one of the branches goes towards minus infinity on the real axis. The other ones meet up at the breakaway point and branch away to a complex conjugate pair. And then as ki goes to infinity, both branches actually cross to the unstable side. Okay? So here is your stable range, stable ki range. So what can we say? Well, you have quite a small range of stable ki. Okay, so notes. Quite a small range of stable system with changing ki. Also dominant poles quite close to the j omega axis. That means I have let's say bad settling time behavior, right? If your dominant poles are very close to the j omega axis, that means you have a slow exponential. That means your settling time will be very large. And if you keep increasing Ki, suddenly the system will become unstable. Okay? So you will have a slow settling time, but then oscillations will start increasing and then the system will become unstable. Okay? Overall, not a very desirable behavior. All right? Bad TS behavior means very large settling time. Okay? Any questions related with the integral controller? Okay? This is more or less what's happening with integral controller by itself. Okay? Because of the larger number of asymptotes, the branches eventually cross to the right half plane, and this is true for any number of asymptotes larger and or equal to 3. Okay, so you usually would like to have one asymptote or two asymptotes. Whenever you have 3 asymptotes, usually you have a picture like this, meaning that you have restricted gain range for which the system is stable, and plus you will be more or less constrained very near the j omega axis, which implies a not so great settling time. Okay? Any questions so far? Arkadaşlar soru var mı?
Yok hocam.
Okay. It is 11:30. So let me say up next.
Bir sorum vardı. Sorabilir miyim abi? Şimdi ödevleri GitHub'a yükledik. Onda sıkıntı yok da bir de ODTÜ Class'ta bir şey açılmış işte ödev yükleme falan diye. Biz o boş kalmasın diye bir de sadece oraya raporu yükledik ama MATLAB faillerini falan GitHub'a da yükledik. Yani istenilen yere yükledik de.
Peki.
ODTÜ Class'taki şeye herhangi bir şey yüklememiz gerekiyor mu yoksa?
Arkadaşlar bu soruyu asistanlarımıza sormanız en uygunu olur. Çünkü ne bekleyerek o ödevi MetuClass'ta açtılar tam olarak bilmiyorum. Ama yani sonuçta tabii ki sorunuz veya cevabı ne olursa olsun herhalde MetuClass'taki açılan yere yüklenebilecek şey belli herhalde. Değil mi?
Ödevin üstünde ilk şey yazmışlar da GitHub'a üye olup GitHub'a yükleyin diye.
Tamam.
Yazmışlar.
Tamam.
O yüzden hani oradakiler değerlendirilecek yazılmış. Biz de boş kalmasın diye rapor yükledik.
Ne düşünerek açıldı bilmiyorum. Sormakta bir fayda var ama safe side'da olmak isterseniz yapılacak şey zaten herhalde ödevinizin metin kısmını veya ödevinizle ilgili her şeyi zipleyip MetuClass'a da yüklemek olabilir.
Anladım.
Tamam. Up next is which is going to be tomorrow is case 4, which is the proportional integral controller. And case 5, which we will also discuss, is the full PID controller. Okay? So we will wrap up the root locus tool, locus-based analysis. Okay? So we will just wrap up our understanding of PI and PID controllers, and then we will move on to how we can actually design numerically those types of controllers. Okay, and I will also this week post 3 videos related with the PID controllers from this website that I keep mentioning to you. Başka soru yoksa arkadaşlar bitireceğim. Soru varsa sorabilirsiniz. Çıkmak isteyen çıkabilir.
İyi günler hocam.
Görüşmek üzere arkadaşlar. Sorusu